I'd like to talk about a common mathematical tool used in physics, the idea of complex numbers, in particular complex polar form for complex numbers. This is in some ways a fairly basic thing, but it's one that a lot of people don't see in introductory math classes, and so I want to give a little talk about it. In particular, I want to talk about complex numbers and a way of understanding them beyond just the basic definition of I being the square root of minus 1. And I'll do that in the context of a simple multiplication problem. I defined two complex numbers, u, 1 plus 3 times I, square root of 3 times I, and v, 1 minus I, and I want to know what the product of those two numbers is. And on some level, this is a really simple problem in complex numbers, because all you need to do is just, u times v is 1 plus square root of 3i times 1 minus I, and you can use your standard algebra tools, FOIL or whatever, to do this. So that's 1 minus 1 times I is I, plus square root of 3i times 1, so plus square root of 3i, and then minus square root of 3i squared. And of course, I squared is minus 1, so this comes out to be just positive square root of 3. So this tells me this is the real part of this. I take the square root of 3 plus 1 is my real part, because those are the real terms. I squared is minus 1, so that's positive square root of 3. And then I can take my imaginary part, square root of 3 minus 1 times I. So square root of 3 times I minus 1 times I gives me, so this is my real part and my imaginary part of this, and there I've multiplied those two numbers. If that were all there were to it, that is all there is to multiplying complex numbers, but it doesn't give me much intuition. It's just an algebra problem. It turns out that complex numbers are a lot deeper than what I've just talked about here. There's a lot more depth and interest to it, and to illustrate that, I'm going to talk about visualizing this whole process in the complex plane. So let's do that. The number u, 1 plus the square root of 3i, I've drawn some axes here for the complex plane, a number line, real number line horizontally, imaginary number line vertically, and so I can visualize these complex numbers. 1 plus the square root of 3i is 1 in its real part, and square root of 3 is 1.73, so 1.73 is about, so here we are. This is u, that dot in the complex plane is u, and v, 1 minus I, 1 real part minus I imaginary part. Here we are, 1 minus I, there is V. U and V, so I visualized those two. This is just drawing a graph right now, there's nothing interesting to it. But by drawing them here, we can start thinking about this in a different way. This can inspire us to say, okay, let's think about this not as Cartesian XY sort of coordinates, but let's think about this in terms of polar coordinates. Polar coordinates, remember, are where instead of measuring xy, we just look at the distance from the origin, that's r, and the angle, theta. And that's polar coordinates. Or down here, I would say that this distance is r, and this angle is theta. Now, of course, I've reused this. Maybe I should label these r for u, and theta for u, and r for v, and theta for v. I don't know, there's not a standard notation for that necessarily. But you think about that, that tells us what these numbers, how we could label these numbers. And you're saying, why is that important? Why talk about polar form? Well, it turns out it's actually pretty straightforward. The magnitude, the absolute value of a complex number, the magnitude of u, for example, if you want to know the magnitude of a complex number, the absolute value of a complex number, it's just the real part squared plus the imaginary part squared, square root. It's the Pythagorean theorem. Square root of 1 squared plus square root of 3 squared. That's the definition of the absolute value, the magnitude of a complex number. And note it's not the square root of 3i squared, because that would be negative. We just do this. And what is that? That's 1 plus 3 is 4, so that's 2. The square root of 4 is 2. And in fact, in this picture, that's what the magnitude is. It's this r, the radius, the distance from the origin, from 0 to the complex number u, to that point. So I guess I could have called this ru. That's what that ru is. It's the absolute value of the complex number. So there's a meaning to that distance in the picture. Similarly, the absolute value of v would be the square root of 1 squared plus, and minus I is minus 1 times I, so that's minus 1 squared. A negative squared is a positive, of course, so that just comes out to be the square root of 2, and that's what I called over there R of E. So this distance here is the square root of 2. So again, we've already got a visual meaning, a meaningful meaning to this polar coordinate part for the radius. For the theta, it's not as obvious what that is. We can define a name for it, right? We can say that the argument of u is what we've called theta u over there in that picture. The argument, arg of u, is that. And to find it, that is the arctangent or inverse tangent. Some people just say tan inverse. I'm saying arctangent because it's a little more explicit. The arctangent of, y over x, y is the imaginary part, so that's the square root of 3 divided by x is the real part, 1. And the arctangent, the inverse tangent, or tangent inverse of the square root of 3 over 1. That is, if you plug that into a calculator, you'll find that that gives you 60 degrees if you're in degree mode, or pi over 3 radians if you're in radian mode. But in any case, we get that answer. So we can calculate that theta, but right now, it's not obvious that there's any meaning to it. It's just a thing in this picture. We'll see in a few minutes that there actually is a deep meaning, but for now, not obvious. Okay, I can do the same thing. What is the argument of v? And that's going to be the arctangent of, let's see, my imaginary part is minus 1. My real part is 1. So arctangent of minus 1 is 45 degrees, or pi over 4 radians. Maybe I should have just written an equal sign here too. So I can get those out. Negative though. Negative 45, negative pi over 4. I should mention the usual things. If you are doing inverse tangent and your x is less than 0, or your real part is less than 0, you have to add pi or add 180 to it to get the right answer. But that's neither here nor there. We'll just stick with this for now. We've got our things we don't have to worry about that subtlety. So okay, we know how to calculate these the angle and the radius, the angle and the absolute value, the magnitude. But why is this important? Why is that useful to me? Well, here's the fun part. Let's do the same thing for u plus v. Let's do the same thing for this u plus v thing. In that case, the magnitude, I haven't written this in, have I? Square root of 3 plus 1 plus the square root of 3 minus 1. This is about, oh, I don't have a good place to write it. U plus v is about 2.73 plus 0.73i. So if I were drawing u plus v in here, it would be 2.73 is about 2 3/4. So it's about here. This is my u times v point on this graph. And okay, u plus v is over here. I guess I can draw, or at least imagine drawing, this line. Here's my r uv. And I guess I can draw theta uv in there in polar form, r and theta. And I can write those down. And again, let's just look at what that is. What is the magnitude of u times v? I can look at this thing. The magnitude of u times v is going to be the square root of, what do I have? Square root of 3 plus 1 squared plus square root of 3 minus 1 squared. Kind of messy, but we can work with that. That comes out to be, oh, it's a mess. It's square root of this squared, so 3 plus 2 square root of 3 plus 1. That's my first term squared, plus 3 minus 2 square root of 3 plus 1. That's my second term squared. And putting them together, the square root of 3 parts actually cancel out, and I end up getting just 3 plus 1 plus 3 plus 1, that's the square root of 8, which is 2 times the square root of 2. And now here's an interesting observation that we can immediately see. 2 times the square root of 2 is exactly equal to the magnitude of u times the magnitude of v, or absolute value of u times absolute value of v. And I guess that makes sense for magnitudes. I'm happy that's true, because that means that the magnitudes multiply of these things. That means that means this absolute value thing is sort of meaningful, because when we multiply two complex numbers together, the magnitude of the result is the product of the two magnitudes. That's true in general, not just for this special case. So we've seen that relationship for the magnitudes. That's neat. What about the angles? Is there anything meaningful to the angle? This is one that's a little messier. I can look at this. The argument of u times v is going to be the arctan of imaginary part over real part. So square root of 3 minus 1 over square root of 3 plus 1. And that's one, maybe you know some way of figuring that out precisely. I didn't at first. I plugged this into some calculator or something, but it turns out it actually gives an exact answer, or at least a very clean answer. It comes out to be 15 degrees, or pi over 12 radians. And this is the place where we suddenly say there's something interesting going on, because 15 degrees is exactly what you get if you take 60 degrees and add negative 45 degrees. This is equal to the argument of u plus the argument of v. And that is suddenly very suggestive. That tells us something kind of cool is going on. And that is also generally true. If you know the arguments of two complex numbers and you multiply them, you multiply the numbers, you just add the arguments together. So what have we learned from this? Multiplying two complex numbers together, u times v, conceptually, what it means is that first we multiply their magnitudes, and then we also add their angles. Put another way, multiplying by a complex number corresponds to a stretch and a rotation in the complex plane. The stretch by the magnitude and the rotation by its angle. So if I started with u and I multiply by v, I'm going to stretch u by a factor of square root of 2, make it that much longer, and then I'm going to rotate it negative 45 degrees. And that's how I get here. So multiplication, complex multiplication, is just multiplication is just a stretch and a rotation. So that's a meaning for complex multiplication right there. And it turns out we can go one step farther and actually see this mathematically. There is a beautiful, elegant, amazing formula called Eulers identity that tells us what it means to take e raised to a complex power. And this is one of the most elegant results in mathematics. It tells us this. So this is Eulers identity. Euler's identity tells us that e to the I theta in radians, theta has to be in radians, always use radians, e to the I theta is equal to the cosine of theta plus I times the sine of theta. That's Euler's identity. And this looks crazy, but this is essentially the defining feature of e to an imaginary number. This is defining feature. And so the neat thing is, cosine plus I sine, this is an angle. Cosine plus I sine looks like an angle in the complex plane. And this makes sense. E to the I theta is something, what is the magnitude of e to the I theta? The absolute value of e to the I theta is equal to the square root of cosine squared theta plus sine squared theta. And there's a trig identity that tells us that is equal to 1. So this is equal to the square root of 1, which is just 1. So this is, e to the I theta is a complex phase. This is the phrase complex phase, it's just an angle. It reflects an angle in the complex plane. Any e to the I theta is going to be something of magnitude 1, and your theta will just take you around a circle of radius 1. E to the I theta lies somewhere on that circle. So if you multiply by an e to the I theta, that rotates by angle theta. That's just telling you, it just points on this circle. That's what this e to the I theta is. Theta is just telling you what your angle is. So here's the cool part. If I wanted to construct the number u, I know its magnitude is 2, and its angle in radians is pi over 3. U is equal to 2 times e to the I pi over 3. Because I start with something of length 2, and by multiplying by e to the I pi over 3, I just rotate by that angle, right? Woof! I get there. Or I could say that v is equal to square root of 2, that was v's magnitude, remember, times e to the minus I pi over 4, because its angle was minus pi over 4. And what does that mean? That means I start with something length square root of 2, so square root of 2 is 1.4 over here, that's my thing, and then multiplying by e to the I pi over 4, minus I pi over 4, I'm just rotating by negative pi over 4 radians, negative 45 degrees. That takes me to here. That's what a complex number is in complex polar form. It is, in general, a complex number any complex number, z can be written as r e to the I theta, where r is its magnitude, its absolute value, and e to the I theta tells you what the angle is. And multiplying those together means exactly the complex number you want. And you find them, this is the absolute value, where r is the absolute value of z, the magnitude of z, and theta is the argument, arg of z. That's the general way for writing this in complex polar form. The cool part is that as soon as we do this, as soon as we write it in this form, all the results we saw earlier are obvious. They come automatically, because then u times v is equal to, well, what was it? It was the magnitude of u times e to the I arg of u, or theta u if I want to call it that, times magnitude of v times e to the I arg of v. And what do? Well, I can rewrite this, I can regroup it a little as magnitude of u times magnitude of v. That's the magnitude of this thing. And then exponent rules. When I multiply two e to the somethings, I just add the exponents. So this is times e to the I arg of u plus I arg of v. Or I suppose I can write that as magnitude of u times magnitude of v times e to the I arg of u plus arg of v, argument of v. And there we go, there we have it. This is saying this whole thing down here is the magnitude of uv. Well, that's supposed to be an absolute value of r. Magnitude, the absolute value of uv. And this whole thing is arg of uv, basically by definition. And this sort of proves the result we saw earlier, that we have now a pattern showing why it is that we multiply two complex numbers, we multiply their magnitudes, and we add their angles. It's because of this complex polar form, this complex exponential form, r e to the I theta, that this works. So in physics, a lot of times, we're going to write complex numbers in this form. And we're going to think of these complex phase factors, these e to the I thetas, as just telling us, hey, this is something about where we are around the complex plane, what our angle is, and multiplying by complex phase just rotates everything by that angle. That's what we do with this complex polar form stuff in physics. It's a really useful tool, and if you haven't seen it before, now you know.